What specific problem does your paper aim to solve regarding pre-training language and vision models in academic settings?
Our paper addresses the significant barrier of high compute costs associated with pre-training language and vision models in academic settings, which often limits the ability of smaller research groups to conduct controlled experiments. We provide transparency regarding the feasibility of pre-training models by empirically measuring and reporting the time necessary to replicate several models on typical academic GPU configurations. By optimizing training methods, we demonstrate that models can be pre-trained using 3x less compute than previously reported, making ambitious experiments more attainable. Additionally, we conduct a cost-benefit analysis to guide researchers in selecting the most effective hardware within their budget constraints. Ultimately, our work aims to empower academic researchers by clarifying the resources available and enabling more informed decisions about their research focus.
Can you explain how your proposed method works? Illustrate the steps involved in conducting the empirical measurements of training time on academic GPU configurations.
Our proposed method for measuring training time on academic GPU configurations involves a systematic empirical approach consisting of 3 key steps. First, we determine the maximum batch size that can fit into the GPU memory by incrementally increasing the batch size until we reach the memory limit. Second, we compute the training step time using this maximum batch size, which may be smaller than the desired size for replication. We achieve this by performing multiple forward and backward passes, accumulating gradients before updating the model parameters. Finally, we extrapolate the training step time across the total number of training steps to estimate the overall training time. This process allows us to benchmark naive settings and explore combinations of efficient training methods to identify optimal configurations that minimize training time. By conducting these empirical measurements, we can provide realistic estimates of training durations for various models on different GPU setups, ultimately enabling more informed decisions for academic researchers.
Could you provide a specific example that showcases how your optimizations allow for efficient training? Walk me through the example, including the training environment and the model you replicated.
In our research, we optimized the training of the Pythia 1B model using 4A100 GPS, which typically would require 41 days to train under naive settings. However, through our efficient training methods, we reduced this time to just 18 days, achieving a 35x speedup. We benchmarked nearly 3,000 configurations and utilized both free lunch methods, such as flash attention and memory saving techniques like activation checkpointing to maximize throughput while minimizing memory consumption. Our empirical measurements involved determining the maximum batch size that could fit in GPU memory and extrapolating the training step time to estimate overall training duration. This example illustrates how our optimizations not only made the training feasible within the constraints of academic hardware, but also significantly reduced the compute resources required, allowing for more ambitious experiments in academic settings.
What are the main advantages of your method over previous approaches to model pre-training, particularly in terms of computational efficiency and accessibility for academic labs?
Our method offers significant advantages over previous approaches to model pre-training by achieving substantial reductions in computational requirements and enhancing accessibility for academic labs. Specifically, we demonstrate that our optimizations allow models like Pythia 1B to be trained in 18 days on just 4A100 GPS, which is 3x less compute than originally reported, making it feasible for labs with limited resources. Additionally, our empirical benchmarks reveal that we can enable training experiments that were previously deemed infeasible, thus broadening the scope of research possibilities for smaller academic groups. Unlike prior works that often required extensive modifications to model architectures or training objectives, our approach maintains replication settings, ensuring that it is model agnostic and can be easily adapted to various deep learning models. Finally, we provide a comprehensive codebase and artifacts that facilitate benchmarking on custom hardware, further democratizing access to efficient pre-training methods in the academic community.
How did you validate the effectiveness of your proposed method? Please discuss the experimental design, types of models used, metrics for performance, and any benchmarks you compared against.
We validated the effectiveness of our proposed method through a comprehensive empirical measurement approach, which involved testing nearly 3,000 configurations across various academic GPU setups. We focused on well-known models, including transformer encoders like RoBERTa and decoders like Pythia, as well as state space models and convolutional networks, ensuring that we replicated their training conditions accurately. Performance metrics included training time in days and compute efficiency, where we benchmarked naive training settings against optimized configurations using both free lunch and memory-saving methods. Our results demonstrated that our optimizations could reduce training time significantly, achieving up to 35 times faster training compared to naive baselines, and we provided detailed comparisons of optimal training times against original reports. Additionally, we released our codebase and artifacts to facilitate further benchmarking and validation by the academic community.
What were the key findings of your research, specifically in terms of the performance of the models you tested and the time or resources saved through your optimizations? What implications do these results have for academic researchers?
Our research revealed that by employing optimizations, we could pre-train models using significantly less compute than previously reported, achieving up to 3x reductions in training time. For instance, we demonstrated that the Pythia 1B model could be trained in just 18 days on 4A100 GPUs, compared to the original estimate of 41 days. Additionally, our empirical benchmarks showed that the naive training times were overly optimistic, highlighting the necessity of our approach for realistic estimates. The implications for academic researchers are profound. Our findings provide a clearer understanding of feasible model training configurations, enabling them to conduct more ambitious experiments within their limited compute budgets. This transparency can help researchers make informed decisions about resource allocation and grant proposals, ultimately fostering a more competitive and diverse research environment.